At the dawn of the 20th century, the atom was no longer a purely philosophical idea, but it was still far from being clearly understood. Scientists knew that matter was made of atoms, and they had begun to imagine what might exist inside them, yet these images were filled with contradictions. One of the most powerful metaphors used at the time was the comparison of the atom to a miniature solar system. In this picture, a dense central nucleus played the role of the sun, while tiny electrons moved around it like planets. This image was not chosen randomly. It came from earlier successes in physics, where simple mechanical models had explained the motion of planets, projectiles, and machines with extraordinary precision. If the same logic worked for the heavens and the earth, many believed it should also work for the atom. This idea gained strength after Ernest Rutherford's famous experiments showed that atoms have a small, positively charged nucleus. Most of the atom, surprisingly, was empty space. This discovery almost demanded a planetary picture. If the positive charge was concentrated at the center, then negatively charged electrons must somehow move around it, held in place by electrical attraction just as planets are held by gravity. The simplicity of this vision was appealing. It suggested that the universe followed a single set of rules, from the largest scales down to the smallest. Nature, in this view, was unified and elegant. Yet beneath this elegant picture, deep problems were hiding. Classical physics, which governed planetary motion, also made very clear predictions about charged particles. An electron moving in a curved path is constantly accelerating, and classical theory stated that any accelerating electric charge must emit radiation. Emitting radiation means losing energy. If electrons in atoms truly behaved like tiny planets, they would continuously radiate energy, spiral inward, and eventually crash into the nucleus. Atoms would collapse in a fraction of a second. Matter would be unstable. Chemistry, solids, life itself would be impossible. And yet, the world around us was stable. Atoms clearly did not self-destruct. This contradiction exposed a crack in the miniature solar system analogy. The image was visually simple, but nature was signaling that something fundamental was missing. At the same time, experimental evidence was piling up that could not be ignored. When scientists studied the light emitted by heated gases, they observed sharp, discrete lines rather than smooth, continuous spectra. Each element produced its own unique pattern of colors, like a fingerprint. These patterns were precise and repeatable, suggesting that atoms could only emit and absorb very specific amounts of energy. This behavior had no place in classical physics, where energy was assumed to vary smoothly. The atom, then, stood at a crossroads. On one side was the comforting familiarity of classical mechanics, which had explained so much. On the other side were stubborn experimental facts that refused to fit. The miniature solar system model captured something real about atomic structure, but it also led directly to conclusions that were clearly false. This tension created an intellectual crisis that demanded a new way of thinking. Into this crisis stepped Niels Bohr, a physicist who was deeply influenced by both experimental results and philosophical reflection. Bohr understood the power of simple models, but he also understood their danger. A model can guide understanding, but it can also mislead if taken too literally. Bohr did not discard the solar system image entirely. Instead, he transformed it. He kept the idea of electrons moving around a nucleus, but he radically altered the rules that governed their motion. Bohr proposed that electrons are allowed to occupy only certain specific orbits. These orbits were not chosen arbitrarily. They were defined by precise conditions related to the electron's energy. While moving in one of these allowed orbits, an electron would not radiate energy, no matter how much this contradicted classical expectations. Radiation occurred only when an electron jumped from one allowed orbit to another. In that jump, energy was emitted or absorbed in discrete packets, which we now call quanta. This move was revolutionary because it broke the direct link between atomic motion and classical mechanics. Bohr effectively said that the atom is not a tiny solar system governed by the same rules as planets. It only resembles one in appearance, not in behavior. The analogy remained useful as a visual aid, but its physical meaning had changed completely. The atom was now a hybrid object, partly classical and partly something entirely new. The success of this idea was immediate and striking. Bohr's model explained the spectral lines of hydrogen with remarkable accuracy. The precise colors of light emitted by hydrogen atoms matched exactly the energy differences between Bohr's allowed orbits. What had once seemed like mysterious patterns now followed from a simple set of assumptions. The miniature solar system, modified by quantum rules, suddenly made sense of experimental reality. This success reshaped how scientists thought about explanation itself. Before Bohr, a good explanation was one that reduced a phenomenon to familiar mechanical principles. After Bohr, explanation became more subtle. It was no longer enough for a model to be intuitively satisfying. It had to match observation, even if that meant abandoning common sense. The atom could still be pictured as a solar system, but that picture had to be handled with care, as a symbolic representation rather than a literal description. The power of the miniature solar system image lay in its ability to connect the unseen world of atoms with everyday experience. People could imagine electrons circling a nucleus just as they imagined planets circling the sun. This visualization helped spread atomic theory beyond specialists and into education and culture. Textbooks, diagrams, and popular science embraced the image, sometimes without emphasizing its limitations. Even today, the Bohr atom remains one of the most recognizable scientific icons. Yet Bohr himself was keenly aware of the model's limits. He never believed that electrons truly followed neat circular paths in the classical sense. For him, the orbits were a mathematical tool, a way of capturing regularities in atomic behavior. As quantum theory developed further, the notion of well-defined electron orbits was replaced by more abstract ideas such as wave functions and probability clouds. The solar system picture gradually lost its central role in professional physics. Despite this, the historical importance of the model cannot be overstated. It represented the first successful attempt to impose order on the chaotic data of atomic spectra. It showed that atoms have an internal structure governed by precise rules, even if those rules defy classical intuition. The miniature solar system was not the final truth about the atom, but it was a crucial stepping stone. More deeply, this story illustrates how scientific understanding often advances. Scientists begin with analogies drawn from familiar experiences. When those analogies fail, they are revised, stretched, or partially abandoned. The atom as solar system idea survived not because it was perfectly accurate, but because it was flexible enough to be transformed. Bohr's genius lay in knowing what to keep and what to let go. The reshaping of the atom also reshaped physics itself. It marked a transition from a world governed by certainty and continuity to one governed by probability and discreteness. The idea that energy comes in fixed amounts challenged deeply held assumptions about nature. It forced physicists to accept that the microscopic world follows rules that have no direct counterpart in everyday life. In this sense, the simple image of a miniature solar system did more than describe the atom. It served as a bridge between old and new ways of thinking. It allowed scientists to step gradually into the quantum world without completely abandoning the language of classical physics. Through Bohr's work, the atom became both familiar and strange, a place where planets seemed to orbit, but obeyed laws unlike anything seen before. The legacy of this transformation extends far beyond atomic theory. Modern technologies, from lasers to semiconductors, depend on the quantum structure of atoms first clarified by Bohr's ideas. Even though the solar system image is no longer considered accurate in detail, its role in guiding discovery remains undeniable. It reminds us that simple stories, when handled wisely, can open the door to profound truths. In the end, the story of the atom as a miniature solar system is not about the correctness of a picture, but about the process of understanding. It shows how science progresses by confronting contradictions, respecting experimental evidence, and daring to modify even the most cherished ideas. Through this process, Niels Bohr transformed a flawed analogy into a powerful insight, reshaping our view of the atom and, with it, our understanding of the physical world. As the miniature solar system picture of the atom gained acceptance, it also began to influence how scientists and the public thought about the structure of reality itself. The atom was no longer an abstract point or an indivisible unit, but a dynamic system with internal motion and order. This shift had philosophical consequences. If matter was mostly empty space held together by invisible forces, then solidity, weight, and permanence were not fundamental properties but emergent ones. Bohr's atom quietly challenged common-sense notions of what it means for something to exist and be stable. At the heart of this challenge was the strange coexistence of motion and stability. In everyday experience, motion usually implies change, decay, or loss of energy. A spinning top slows down, a swinging pendulum eventually comes to rest. Yet in Bohr's atom, electrons moved endlessly without losing energy as long as they remained in allowed states. This idea was deeply unsettling to physicists trained in classical thinking. It suggested that nature, at the smallest scale, had built-in rules that protected certain forms of motion from decay. Stability was no longer something that had to be explained mechanically, it was imposed by quantum conditions. This notion helped explain one of the most basic facts of existence: why matter lasts. The solidity of tables, the reliability of chemical reactions, and the persistence of living structures all depend on the stability of atoms. By linking this stability to discrete energy levels, Bohr provided a conceptual anchor for understanding why the material world does not simply dissolve. The miniature solar system, corrected by quantum rules, became a symbol of order hidden within apparent emptiness. The visual simplicity of the model also played a crucial role in education. At a time when quantum ideas were becoming increasingly abstract, Bohr's atom offered something concrete to hold on to. Students could draw it, label it, and imagine it. This did not mean they fully understood quantum mechanics, but it gave them an entry point. The image functioned as a teaching tool that balanced accessibility with depth. Even when later theories replaced it, the Bohr model often remained the first step in learning about atomic structure. However, this educational success carried a risk. The more familiar the image became, the more tempting it was to treat it as literal truth. Many misunderstandings about atoms stem from taking the solar system analogy too seriously. Electrons do not actually travel in neat circular paths like planets, nor do they have precise locations at all times. Bohr himself emphasized that the model was a representation, not a photograph of reality. It was a language for talking about atomic behavior, not a final description. This distinction between model and reality became one of the central lessons of modern physics. Bohr argued that our descriptions of nature are always shaped by the concepts and tools we use. When we move into realms far removed from everyday experience, those concepts must be used with caution. The atom forced physicists to confront the limits of visualization and language. The miniature solar system was useful precisely because it was simple, but its simplicity also meant it could not capture everything. As quantum theory evolved, the shortcomings of the Bohr model became increasingly clear. More detailed experiments revealed fine structures in spectral lines that the model could not explain. The behavior of atoms in magnetic fields, the interactions between multiple electrons, and the wave-like properties of particles all demanded a more sophisticated framework. New theories replaced fixed orbits with probability distributions and mathematical functions that resisted easy visualization. Yet even as the Bohr model was surpassed, its conceptual impact remained. It marked the moment when physics decisively broke with the idea that all natural phenomena could be understood through continuous motion and deterministic laws. The atom as solar system analogy, once corrected by quantum jumps, opened the door to a universe governed by probabilities and discrete events. This shift did not only affect atomic physics, it reshaped the entire scientific worldview. The miniature solar system also influenced how scientists thought about scale. Before Bohr, it was tempting to believe that smaller systems were simply scaled-down versions of larger ones. The same laws applied everywhere, just with different numbers. Bohr showed that this assumption was false. The microscopic world has its own logic. Similarities in appearance do not guarantee similarities in behavior. This insight became a guiding principle in many areas of science, reminding researchers to be wary of naive extrapolation. Culturally, the image of the atom captured the imagination of an era fascinated by progress and hidden forces. Atomic diagrams appeared in art, advertising, and architecture. They symbolized modernity, knowledge, and the promise of scientific mastery. Even people with little understanding of physics recognized the symbol of electrons orbiting a nucleus as a sign of advanced science. Bohr's work, filtered through popular representation, became part of collective consciousness. At the same time, the atom's new image carried a sense of mystery and unease. If matter was mostly empty space, what did that say about the solidity of the world? If energy came in jumps, what did that imply about continuity and causality? These questions spilled beyond physics into philosophy and even literature. The atom became a metaphor for the hidden complexity beneath ordinary appearances. Bohr himself embraced this broader perspective. He believed that the lessons of atomic physics extended beyond science. The need to use complementary descriptions, the recognition of limits to certainty, and the acceptance of paradox all reflected a deeper understanding of knowledge itself. The miniature solar system, modified and constrained, exemplified this attitude. It was both true and not true, useful and misleading, depending on how it was applied. This nuanced view contrasted sharply with earlier scientific optimism that sought simple, complete explanations. Bohr's atom suggested that nature might resist full transparency. We could predict outcomes with great accuracy, but our mental pictures would always be approximations. The goal of science shifted from revealing an ultimate mechanical reality to constructing reliable frameworks for understanding and prediction. In practical terms, the ideas introduced through Bohr's model laid the groundwork for countless technological advances. Understanding atomic energy levels made it possible to develop lasers, atomic clocks, and modern electronics. These technologies rely on precise control of electron transitions, the very jumps Bohr introduced to explain spectral lines. The miniature solar system may no longer be used in advanced calculations, but its core insight lives on in applied science. Looking back, it becomes clear that the power of the first keynote lies not in the literal truth of the solar system analogy, but in its transformative role. It reshaped the questions scientists asked and the answers they were willing to accept. It demonstrated that intuition must sometimes yield to evidence, and that simplicity must sometimes be sacrificed for accuracy. At the same time, it showed that chosen simplicity can guide discovery even when it is ultimately transcended. The story of Niels Bohr and the atom thus illustrates a central pattern in the history of science. Progress often begins with a familiar image that brings the unknown into focus. That image is tested, strained, and eventually revised. What remains is not the picture itself, but the deeper insight it enabled. The miniature solar system helped scientists see that atoms are structured, stable, and governed by precise rules, even if those rules defy everyday logic. In the end, the atom did not turn out to be a tiny solar system, but thinking of it that way changed everything. It forced physics to confront its own limitations and inspired a new way of understanding the natural world. Through this simple yet radical idea, Bohr helped open the path to quantum mechanics and forever altered our conception of matter, motion, and reality itself. At the turn of the 20th century, classical physics stood as one of humanity's greatest intellectual achievements. It explained the motion of planets, the behavior of waves, the flow of heat, and the mechanics of everyday objects with astonishing accuracy. The laws formulated by Newton and refined over centuries gave scientists deep confidence that nature was ultimately predictable, continuous, and orderly. According to this worldview, if one knew the forces acting on a system and its initial conditions, one could in principle calculate its future behavior with perfect precision. This confidence shaped how scientists approached every new problem, including the structure of the atom. When researchers first tried to understand atoms using classical ideas, it seemed natural to extend familiar laws downward to smaller scales. If gravity governed planets, electric forces governed charged particles. If motion followed precise trajectories in space and time, then electrons should do the same. Early atomic models rested firmly on this assumption. The atom was imagined as a tiny mechanical system whose parts obeyed the same principles as larger objects, just on a smaller scale. However, as experiments became more precise, cracks began to appear in this elegant picture. One of the earliest and most troubling failures of classical physics emerged from the study of radiation. According to classical theory, an object heated to a high temperature should emit electromagnetic radiation across a continuous range of frequencies. The intensity of this radiation was expected to increase smoothly with frequency. Yet experiments revealed something deeply unsettling. At high frequencies, classical calculations predicted infinite energy output, a result that was clearly impossible. This contradiction, later known as the ultraviolet catastrophe, showed that classical physics could not even correctly describe something as basic as how hot objects glow. At the atomic level, the problems became even more severe. Electrons are electrically charged, and classical electrodynamics made very specific predictions about their behavior. Any charged particle that accelerates should emit radiation and lose energy. In an atom, electrons moving in curved paths around a nucleus are constantly accelerating. According to classical laws, they should continuously radiate energy, slow down, and spiral inward. This process would happen extremely quickly, causing atoms to collapse almost instantly. The very existence of stable matter contradicted this prediction. This was not a small discrepancy that could be fixed with minor adjustments. It was a fundamental failure. If classical physics were correct at all scales, atoms could not exist in a stable form. Chemistry would be impossible. The solid world would dissolve. The fact that matter was stable was not an incidental detail, it was the most basic feature of reality. Classical theory, despite its success elsewhere, simply could not account for it. At the same time, spectroscopy provided another devastating challenge. When scientists examined the light emitted or absorbed by atoms, they found that it consisted of sharp, discrete lines at specific frequencies. Each element produced its own unique pattern. Classical physics, which treated energy as a continuous quantity, had no way to explain why atoms would prefer certain frequencies and reject others. There was no reason, within classical theory, for energy exchange to be restricted to specific values. Attempts were made to save the classical framework. Some physicists hoped that more detailed mechanical models or hidden interactions would resolve the discrepancies. Others suggested that the atom might be more complex than initially thought, with internal structures that somehow stabilized electron motion. But these efforts consistently failed. No matter how the equations were adjusted, classical physics could not simultaneously explain atomic stability and spectral discreteness. The growing list of contradictions forced physicists to confront an uncomfortable possibility. The laws that governed everyday objects might not apply unchanged at microscopic scales. This idea was deeply unsettling. Classical physics was not just a collection of equations, it represented a worldview built on continuity, determinism, and visualizable motion. To abandon it, even partially, felt like giving up on the very idea that nature was understandable. One of the most profound issues was the concept of continuity. Classical physics assumed that physical quantities such as energy, position, and momentum could vary smoothly. There were no inherent gaps or jumps. Yet atomic experiments suggested the opposite. Energy appeared to be exchanged in discrete amounts. Transitions happened suddenly, not gradually. This behavior had no place in classical theory and could not be derived from it. Another failure lay in the classical treatment of light. Light was understood as a wave, and this description successfully explained phenomena like interference and diffraction. But experiments such as the photoelectric effect showed that light sometimes behaved as if it consisted of particles delivering energy in lumps. Classical wave theory predicted that light intensity, not frequency, should determine the energy transferred to electrons. Experiments showed the opposite. Again, classical reasoning led to incorrect conclusions. These failures revealed a deeper problem. Classical physics relied heavily on intuitive pictures drawn from everyday experience. Objects had definite positions and velocities. Causes preceded effects in a smooth and predictable way, but the atomic world did not conform to these intuitions. Electrons did not behave like tiny balls following well-defined paths. Energy did not flow like a continuous fluid. The microscopic world seemed to operate according to principles that were fundamentally alien to classical thinking. The resistance to abandoning classical ideas was strong, and understandably so. For centuries, physics had advanced by refining and extending existing laws. The notion that an entirely new framework was needed felt extreme. Many scientists hoped that classical physics was still fundamentally correct, and that the observed anomalies were temporary gaps in understanding. But as evidence accumulated, this position became increasingly difficult to defend. What made the situation particularly challenging was that classical physics continued to work extremely well in many contexts. It did not suddenly become wrong. It still accurately described macroscopic motion, engineering systems, and astronomical phenomena. The failure was selective. Classical laws worked at large scales but broke down at small ones. This selective failure raised deep questions about the scope and limits of scientific theories. Gradually, physicists began to accept that the atom required new principles. This acceptance did not come all at once. It emerged through a series of conceptual shocks, each revealing another way in which classical reasoning failed. The stability of atoms, the discreteness of spectra, the behavior of radiation, and the interaction between light and matter all pointed in the same direction. The classical picture was incomplete. This realization marked a turning point in the history of science. It showed that even the most successful theories could have boundaries beyond which they no longer applied. It also demonstrated that progress sometimes requires not refinement, but radical change. The failure of classical physics at the atomic level was not a sign of weakness, but a sign of its limits. The collapse of classical explanations did more than create problems, it created opportunity. By exposing what could not be explained, experiments illuminated the path forward. The contradictions forced physicists to question their assumptions about nature, measurement, and explanation. They prepared the ground for new ideas that would eventually reshape physics. The breakdown of classical physics also transformed the role of experiment. No longer could theory confidently predict outcomes based solely on established laws. Experiments became judges that could overturn deeply held beliefs. When theory and observation conflicted, it was theory that had to yield. This shift reinforced a more humble view of scientific knowledge, one in which models are tools rather than final truths. As classical physics faltered, a new way of thinking began to emerge. Energy would no longer be treated as infinitely divisible. Motion would no longer always be described by precise trajectories. Probability would replace certainty in describing microscopic events. These ideas were initially met with skepticism, but they directly addressed the failures that classical physics could not overcome. The inability of classical theory to explain the atom was therefore not merely a technical problem. It was a conceptual crisis that challenged the foundations of physics. It forced scientists to recognize that nature might not conform to human intuition, and that understanding the universe might require accepting ideas that defy common sense. In hindsight, the failure of classical physics appears almost inevitable. Classical laws were derived from observations of the macroscopic world, where quantum effects are negligible. Expecting them to apply unchanged at atomic scales was an assumption, not a necessity. The atom revealed that the universe is layered, with different rules dominating at different scales. This realization reshaped the scientific mindset. It taught physicists to ask not only whether a theory works, but where it works and why. It highlighted the importance of domain-specific laws and the danger of assuming universal applicability. Classical physics remained true within its proper limits, but it was no longer seen as the final word on nature. The story of classical physics, failing at the atomic level, is therefore a story of growth rather than defeat. By reaching its limits, classical theory made room for deeper understanding. Its failures were not errors to be erased, but signals pointing toward a richer and more accurate description of reality. Through these failures, science learned one of its most important lessons, that the universe is more subtle than any single framework can capture, and that progress often begins where certainty ends. As the inadequacy of classical physics became impossible to ignore, the scientific community entered a period of deep uncertainty and intellectual tension. Physicists were faced with a troubling paradox. On one hand, the classical framework had proven itself again and again in explaining the visible world. On the other hand, when applied to atoms and radiation, it produced results that were not just slightly inaccurate but fundamentally wrong. This tension forced scientists to confront a difficult question. Could a theory be both profoundly successful and profoundly incomplete at the same time? The struggle to answer this question reshaped the identity of physics itself. Until then, many believed that scientific progress was a process of steady accumulation, where new discoveries simply added detail to an already solid foundation. The atomic crisis shattered this belief. It showed that progress could also involve rupture, where old ideas must be revised or even abandoned. This realization was psychologically difficult for many physicists, especially those who had built their careers on classical principles. Accepting the failure of classical explanations at the atomic level felt like standing on unstable ground. One of the most unsettling aspects of this failure was its impact on determinism. Classical physics promised a universe governed by strict cause and effect. If the present state of a system was known exactly, its future could be calculated precisely. This idea was not just scientific, it carried philosophical weight. It suggested a universe that was, in principle, fully predictable. Atomic phenomena undermined this promise. The behavior of electrons and the emission of radiation did not follow smooth, predictable paths. Instead, they seemed to involve abrupt changes and statistical patterns. This shift toward probabilistic behavior challenged deeply held assumptions about reality. Many physicists initially resisted it, hoping that probability merely reflected ignorance rather than fundamental uncertainty. They believed that hidden variables or undiscovered mechanisms would eventually restore determinism. But as experimental evidence continued to align with probabilistic predictions, this hope began to fade. The failure of classical physics was not just about incorrect equations, it was about the limits of certainty itself. Another major consequence of classical breakdown was the changing role of visualization. Classical physics relied heavily on mental pictures, trajectories, forces, waves, and fields that could be imagined in space and time. Atomic phenomena resisted such visualization. Electrons did not behave like tiny planets or billiard balls. Light did not behave purely as a wave or purely as a particle. The more physicists tried to force atomic behavior into classical images, the more contradictions they encountered. This forced a profound shift in how scientific understanding was defined. Instead of asking whether a theory could be visualized, physicists began to ask whether it could accurately predict outcomes. Mathematical consistency and experimental agreement became more important than intuitive clarity. This marked a departure from centuries of scientific tradition, where understanding was closely tied to visualization. The atomic crisis showed that nature does not owe humanity intuitive explanations. The collapse of classical explanations also altered how scientists thought about measurement. In classical physics, measurement was assumed to reveal pre-existing properties without disturbing the system. Atomic experiments showed that this assumption was no longer valid. The act of measuring atomic systems often changed their behavior. This realization blurred the boundary between observer and observed, further weakening classical assumptions about objectivity and independence. As these ideas took hold, a new scientific humility began to emerge. Physicists became more cautious about making absolute claims about reality. They recognized that theories are models designed to organize experience, not mirrors that perfectly reflect nature. This humility did not weaken science, it strengthened it. By acknowledging limits, physicists opened the door to more flexible and powerful frameworks. The failure of classical physics also highlighted the importance of empirical evidence over philosophical comfort. Many of the new ideas that emerged were deeply counterintuitive and even disturbing, yet they worked. They explained observations that classical physics could not. This forced scientists to choose between intuition and evidence. And again, evidence won. The atomic crisis became a powerful reminder that nature sets the rules, not human expectation. In practical terms, this shift changed how research was conducted. Experiments became more precise and more central to theory development. Instead of confirming existing laws, experiments increasingly served to test the boundaries of understanding. Unexpected results were no longer treated as nuisances but as opportunities. Anomalies became clues rather than errors. The selective failure of classical physics also led to a more nuanced understanding of scientific truth. A theory could be true within a certain domain and false outside it. This idea, now taken for granted, was revolutionary at the time. It meant that science was not a single, unified structure built on unchanging laws, but a layered system of models, each valid under specific conditions. Classical physics did not disappear, it was reinterpreted as an approximation that works extremely well at large scales. This layered view of reality had far-reaching consequences beyond physics. It influenced chemistry, biology, and even social sciences by encouraging researchers to think in terms of levels of description. What works at one scale may fail at another. Complexity can emerge from simple rules, and new laws can arise that are not obvious from lower-level descriptions. The atomic crisis thus contributed to a broader shift in scientific thinking. The emotional dimension of this transformation should not be underestimated. For many physicists, the failure of classical explanations felt like a loss. It marked the end of a dream in which the universe was fully comprehensible through simple mechanical laws. At the same time, it generated excitement. New questions emerged, new tools were developed, and a new generation of scientists found itself exploring uncharted territory. Uncertainty became a source of creativity rather than fear. The breakdown of classical physics also reshaped scientific collaboration. Solving the atomic puzzle required the combined efforts of theorists and experimentalists across different countries and disciplines. No single mind or method could resolve the crisis alone. This collaborative spirit accelerated the development of new ideas and helped establish physics as a truly international enterprise. As new principles began to replace classical assumptions, the failure of old ideas became a foundation rather than an embarrassment. The contradictions that once seemed disastrous were reinterpreted as signs of deeper structure. The inability of classical physics to explain the atom was no longer seen as a problem to be hidden, but as a milestone in the evolution of knowledge. Looking back, it becomes clear that the atomic crisis was not about the destruction of classical physics, but about its transformation. Classical laws remain indispensable for understanding much of the world. Bridges stand, machines work, and planets move according to principles discovered centuries ago. What changed was the recognition that these laws are not universal in scope. The lesson of this failure continues to shape modern science. It reminds researchers to remain open to revision, to respect empirical evidence, and to accept that even the most successful theories may have limits. It also highlights the creative power of failure. When existing ideas break down, new possibilities emerge. In the context of atomic theory, the collapse of classical explanations cleared the path for a radically new understanding of matter. It forced physicists to rethink energy, motion, and measurement. It challenged assumptions about determinism and objectivity. Most importantly, it demonstrated that nature can behave in ways that defy common sense while remaining perfectly consistent and lawful. The story of classical physics failing at the atomic level is therefore a story of intellectual courage. It required scientists to admit that their most trusted tools were insufficient and to venture into unfamiliar conceptual territory. This willingness to confront failure rather than deny it is one of the defining strengths of science. Ultimately, the atom taught physicists that understanding the universe is not about preserving comfort or tradition. It is about following evidence wherever it leads, even when that path overturns long-held beliefs. The failure of classical physics was not an end, but a beginning, marking the moment when humanity's understanding of nature became deeper, richer, and more honest than ever before. At a time when physics was struggling to explain the strange behavior of atoms, one idea emerged that was both simple and radical. It did not come from complex machinery or exotic experiments, but from a careful reading of what nature was already revealing. The problem was clear. Atoms emitted and absorbed energy in very specific ways, yet existing theories could not explain why. Instead of forcing old rules onto new phenomena, a new approach was needed, one that accepted limitation as a feature of nature rather than a failure of understanding. The central difficulty lay in energy itself. Classical physics treated energy as something smooth and continuous, like water flowing through a river. An object could gain or lose any amount of energy, no matter how small. This assumption worked well for everyday experiences and large-scale systems. However, atomic experiments repeatedly contradicted this idea. When atoms interacted with light, they did not respond gradually. They responded selectively. Certain energies were allowed, others forbidden. There were gaps where nothing happened. This pattern was impossible to ignore. Spectral lines provided precise evidence. Each element produced its own unique set of colors, and these colors never shifted randomly. They appeared at exact, repeatable positions. This meant that atoms could only change their internal energy by specific amounts. The implication was profound. Energy inside atoms was not continuous. It came in steps. The bold insight was to accept this discreteness as fundamental. Instead of viewing it as a flaw in measurement or an experimental artifact, it was treated as a rule of nature. The atom was no longer a system that could exist in any energy state whatsoever. It was restricted to a limited set of allowed states. These states were stable, and the atom could remain in them indefinitely without radiating energy. This idea directly addressed one of the greatest contradictions of atomic theory: stability. If electrons behaved according to classical rules, atoms would collapse. By introducing fixed energy states, stability was no longer mysterious. An electron in one of these states had no lower energy available unless it made a sudden transition. There was no gradual leaking of energy. Stability was built into the structure of the atom itself. The concept of fixed energy levels also provided a natural explanation for light emission. When an atom absorbed energy, one of its electrons could move to a higher allowed state. This was not a smooth climb but a jump. When the electron later returned to a lower state, the energy difference was released as light. The color of that light depended exactly on the difference between the two energy states. This simple rule explained why atoms produced sharp spectral lines instead of continuous spectra. What made this idea especially striking was its departure from classical intuition. In everyday life, motion and change are continuous. We do not teleport from one place to another, we move through all intermediate positions. The idea that an electron could vanish from one state and reappear in another without passing through the space in between seemed absurd. Yet experiments supported exactly this behavior. Nature, it appeared, did not care about human expectations. The acceptance of fixed energy levels required a new way of thinking about motion. Electrons were no longer described as tiny particles following precise paths in space and time. Instead, their behavior was defined by which states they could occupy and how they could transition between them. The emphasis shifted from trajectories to conditions. What mattered was not where the electron was at every moment, but which energy state it belonged to. This shift also changed the meaning of explanation in physics. Previously, to explain something meant to describe its motion step by step using forces and equations. Now, explanation meant identifying allowed states and rules for transitions. It was less about telling a mechanical story and more about identifying patterns and constraints. The atom was understood not as a machine, but as a system governed by selection rules. One of the most remarkable aspects of this approach was how much it explained with so little. By assuming only that energy levels were fixed and that transitions between them involved discrete amounts of energy, a wide range of experimental data suddenly made sense. Hydrogen spectral lines, which had puzzled scientists for decades, could be calculated with stunning accuracy. The agreement between theory and experiment was too precise to dismiss as coincidence. This success suggested that discreteness was not a minor detail, but a foundational principle. Energy at the atomic scale was quantized. This word, derived from the idea of quantity, captured the essence of the discovery. Energy came in packets, not streams. The atom was not free to behave arbitrarily. It was constrained by rules that allowed only certain possibilities. The introduction of fixed energy levels also had deep implications for how change occurred in nature. Transitions between states were instantaneous. There was no gradual transformation from one energy level to another. This meant that some aspects of atomic behavior could not be described in terms of continuous time evolution. Events happened abruptly, without intermediate stages that could be observed or described. This raised unsettling questions. What happened during the jump? How did the electron know where to go? These questions could not be answered within the framework that introduced the jumps in the first place. And yet, the framework worked. It predicted outcomes with extraordinary accuracy. Physics was forced to confront a new reality. A theory could be successful even if it did not provide a complete picture of what was happening behind the scenes. This acceptance marked a turning point. Instead of demanding that theories provide intuitive explanations, physicists began to prioritize predictive power and consistency with observation. If a model correctly described what could be measured, it was considered valid even if it left deeper questions unanswered. This pragmatic attitude became a defining feature of modern physics. The idea of fixed energy levels also reshaped how physicists thought about possibility and impossibility. Certain transitions simply could not occur because there were no allowed states connecting them. This meant that nature had built-in restrictions. Not everything that could be imagined could actually happen. The structure of reality was selective. These restrictions explain not only atomic spectra but also chemical behavior. The way atoms bonded, reacted, and formed molecules depended on their energy levels. Chemistry, which had long been empirical, began to find a theoretical foundation. The periodic table, once a mysterious arrangement, could be understood in terms of how electrons filled available energy states. Beyond science, the idea of discrete states influenced philosophy. It challenged the assumption that continuity was a fundamental feature of reality. If energy, one of the most basic physical quantities, was quantized, what else might be discrete? Space, time. These questions would later become central to deeper theories, but their roots lay in the simple observation that atoms do not allow arbitrary energies. The emotional impact of this idea on the scientific community was mixed. Some saw it as an elegant solution to long-standing problems. Others viewed it as an admission of ignorance, a temporary fix that avoided deeper explanation. The notion of unexplained jumps felt unsatisfying to those trained in classical reasoning. Yet repeated experimental confirmation made it impossible to dismiss. What ultimately secured acceptance was not philosophical argument, but practical success. Calculations based on fixed energy levels consistently matched observed data. No classical alternative could achieve the same results. Nature had spoken clearly, and physics had to listen. This shift also changed how scientists viewed the relationship between theory and reality. Theories were no longer seen as direct descriptions of what exists, but as frameworks for organizing experience. An energy level was not something that could be seen or touched. It was a concept that captured regularities in behavior. This more abstract view of theory allowed physics to move forward despite the loss of intuitive imagery. In retrospect, the introduction of fixed energy levels appears inevitable, given the evidence. But at the time it required intellectual courage. It meant accepting that the microscopic world follows rules fundamentally different from those governing everyday life. It meant letting go of the comforting idea that everything could be understood as scaled-down mechanics. This change did not happen overnight. It unfolded gradually as each successful prediction reinforced confidence in the new approach. Slowly, the idea of quantized energy became a cornerstone of atomic theory. It prepared the ground for even more radical ideas, such as wave-particle duality and probabilistic behavior. The significance of fixed energy levels extends far beyond atomic physics. It represents a shift in how humanity understands order in nature. Order was no longer associated solely with smoothness and continuity. It could also arise from constraint and discreteness. The atom was orderly not because it could do anything, but because it could do only a few specific things. This insight continues to shape modern science and technology. From lasers to digital electronics, many of the tools that define contemporary life depend on controlled transitions between discrete energy states. What began as an attempt to explain spectral lines became a foundation for entire industries. At its core, the idea of fixed energy levels reflects a deeper lesson about knowledge itself. Understanding does not always mean visualizing. Sometimes it means accepting patterns without insisting on familiar explanations. The atom taught physicists that reality can be precise without being intuitive, lawful without being mechanical. The acceptance of discrete energy states marked a decisive step away from classical thinking. It resolved contradictions that had plagued atomic theory and opened a path toward a new understanding of matter. In doing so, it demonstrated that simplicity and radical change can coexist, and that the most profound revolutions often begin with the smallest observations. As the idea of discrete energy states settled into the foundations of atomic theory, its implications continued to unfold in ways that reshaped not only physics, but the very meaning of explanation and reality. What began as a practical solution to experimental puzzles gradually revealed itself as a profound shift in how nature operates at its most fundamental level. The atom was no longer a stage for continuous motion, but a system governed by permission and restriction, where only certain states were allowed and everything else was forbidden. One of the most striking consequences of this view was the new understanding of change itself. In the classical world, change is something that unfolds smoothly. Objects accelerate, slow down, heat flows from hot to cold, and systems evolve through every intermediate stage. At the atomic level, this picture broke down completely. Change happened through sudden transitions. An atom did not gradually emit a photon, it either did or it did not. There was no half emission, no partial jump. This forced physicists to accept that continuity, long regarded as a hallmark of physical law, was not universal. This realization altered how time was conceptualized in microscopic processes. Classical physics treated time as a continuous parameter through which systems evolved smoothly. Atomic transitions, however, suggested events that were localized in time yet lacked an internal timeline that could be described. The question of what occurred during a transition became meaningless within the theory. Physics had to accept that some processes could be characterized only by their initial and final states, not by a detailed story of what happened in between. This shift challenged the traditional notion of causality. In classical thinking, causes lead to effects through a continuous chain of events. In atomic behavior, the link between cause and effect appeared less direct. An atom absorbed energy and later emitted it, but the precise moment and manner of emission could not be predicted with certainty. Only probabilities could be assigned. This did not mean that nature was chaotic or lawless, but that its laws operated differently than previously assumed. The emergence of probability as a central concept marked another departure from classical ideas. Fixed energy levels impose structure, but they did not determine when transitions would occur. Two identical atoms in identical conditions could behave differently. One might emit radiation while the other remained unchanged. The theory could predict the likelihood of emission, but not the exact outcome of a single event. This statistical character was not due to experimental limitations, it was intrinsic to the behavior of atoms. This was deeply unsettling to many physicists. Probability had long been associated with ignorance, not with fundamental law. The idea that randomness might be built into nature itself seemed almost heretical. Yet every attempt to restore certainty failed. Experiments consistently supported probabilistic predictions. The discrete energy framework, combined with statistical rules, described atomic behavior with extraordinary accuracy. The universe, it seemed, was lawful but not deterministic in the classical sense. The consequences of this realization extended to the concept of measurement. Measuring an atomic system was no longer a passive act of observation. The very act of probing an atom could trigger transitions between energy states. Measurement and change became inseparable. This blurred the boundary between observer and observed, a boundary that classical physics had treated as clear and absolute. The atom taught physicists that knowledge itself has physical consequences. As these ideas spread, they began to influence the broader structure of physical theory. Mathematical descriptions became more abstract, focusing on allowed states and transition rules rather than trajectories and forces. The language of physics shifted from motion to configuration, from dynamics to structure. This abstraction made theories harder to visualize, but more powerful in prediction. The notion of discrete energy states also transformed how physicists understood stability and instability. Stability was no longer a dynamic balance of forces, but a consequence of constraint. An atom in its lowest allowed state could not lose energy because there was nowhere lower to go. Instability arose only when transitions were permitted. This concept proved remarkably robust and was extended to many other systems beyond simple atoms. In chemistry, the implications were revolutionary. Chemical reactions could now be understood as rearrangements of electrons between allowed states. The strength of chemical bonds, the shape of molecules, and the patterns of reactivity all traced back to energy level structure. What had once been an empirical science began to acquire a deep theoretical foundation. The behavior of matter at everyday scales was linked directly to quantized states at the atomic level. The success of these ideas also reshaped the criteria for scientific explanation. Previously, a good explanation was one that reduced phenomena to familiar mechanical processes. Now, explanation meant identifying the mathematical structure that governed possible outcomes. Intuition became secondary to consistency and predictive accuracy. This did not make physics less meaningful, but it did make it more demanding. Understanding required accepting concepts that could not be directly pictured. This new standard of explanation had philosophical consequences. It challenged the idea that reality must be comprehensible in human terms. The atom suggested that the universe operates according to principles that are precise yet alien to everyday thought. Human intuition, shaped by macroscopic experience, was no longer a reliable guide at microscopic scales. Knowledge had to be earned through careful reasoning and experiment, not assumed through analogy. Despite its abstract nature, the framework built on discrete energy states proved extraordinarily fertile. It became the foundation for technologies that would define the modern world. Lasers rely on controlled transitions between energy levels. Semiconductors function because electrons occupy bands of allowed and forbidden energies. Atomic clocks measure time using transitions so precise that they lose only seconds over millions of years. These applications demonstrate that even the most counterintuitive ideas can have practical power. The acceptance of discrete energy states also influenced how future theories were developed. It encouraged physicists to think in terms of quantization more broadly. If energy was quantized, perhaps other quantities were as well. This line of thinking led to the quantization of angular momentum, the introduction of wave-particle duality, and eventually the development of a full quantum mechanical framework. Each step built upon the willingness to abandon classical continuity. Importantly, the transition to this new view did not erase the achievements of classical physics. Instead, it placed them within a larger context. Classical laws emerged as approximations that work extremely well when energy levels are closely spaced or when systems involve many particles. The new theory explained why classical physics works where it does and fails where it must. This reconciliation strengthened confidence in both frameworks. The emotional journey of the scientific community during this transition was complex. There was excitement at the power of the new ideas, frustration at their strangeness, and humility in the face of nature's refusal to conform to expectation. Many physicists struggled with the loss of intuitive clarity, but most came to accept that clarity is not the same as truth. The success of the theory demanded respect, regardless of personal discomfort. Over time, what once seemed radical became normal. Students learned about energy levels as a basic fact of nature. The idea of quantum jumps, once controversial, became routine. This normalization illustrates how scientific revolutions eventually fade into the background of accepted knowledge. What remains is not the shock of the new, but the expanded understanding it provides. The deeper lesson of discrete energy states lies in what they reveal about the structure of reality. Nature is not infinitely flexible. It is selective, constrained, and precise. Possibility is not continuous but structured. These constraints are not limitations imposed by theory. They are features of the world itself. The atom behaves as it does not because physicists describe it that way, but because it cannot behave otherwise. This insight has influenced thinking far beyond physics. It has shaped discussions about complexity, emergence, and the limits of reductionism. It suggests that higher-level phenomena arise not from infinite freedom, but from restricted possibilities. Order emerges from limitation. This idea resonates in fields ranging from biology to information theory. Looking back, the acceptance of discrete energy states stands as one of the most significant turning points in the history of science. It resolved contradictions that had stalled progress and opened pathways that continue to be explored. It demonstrated that progress sometimes requires letting go of deeply held assumptions and embracing ideas that challenge intuition. The atom, once thought to be indivisible and simple, revealed itself to be governed by subtle and exact rules. These rules were not mechanical in the classical sense, but they were no less real. They described a world where change occurs through jumps, stability arises from constraint, and knowledge is probabilistic rather than absolute. In the end, the shift to fixed energy states taught physicists a profound lesson about understanding. Reality does not promise comfort or simplicity. It offers patterns that must be discovered, not assumed. By accepting discreteness where continuity had once reigned, physics gained a deeper, more honest picture of nature. This willingness to follow evidence beyond intuition remains one of science's greatest strengths and its most enduring legacy. Light played a decisive role in uncovering the hidden structure of the atom, long before anyone could directly observe what was happening inside it. In many ways, light became the language through which atoms revealed their secrets. By carefully studying how atoms interact with light, scientists discovered patterns that could not be explained by existing theories and were forced to rethink the nature of matter itself. What seemed at first like simple colors turned out to be precise messages encoded by atomic structure. When atoms are heated or energized, they emit light. At first glance, one might expect this light to form a smooth, continuous spectrum similar to sunlight spread out through a prism. Classical physics predicted exactly this kind of behavior. If atoms behaved like tiny mechanical systems, their energy should vary smoothly, and so should the light they emit. However, experiments told a very different story. Instead of a continuous rainbow, scientists observed sharp, isolated lines of color. These lines appeared at exact positions and never shifted randomly. Each chemical element produced its own unique pattern, as distinctive as a fingerprint. These spectral lines were among the most important clues in the history of atomic physics. They suggested that atoms could only emit light of certain energies and no others. Since the color of light is directly related to its energy, this meant that the internal energy of atoms was somehow restricted. Light was not just something atoms produced, it was a direct reflection of what was happening inside them. The atom was revealing its internal rules through the colors it allowed to escape. At first, these observations were deeply puzzling. Classical theories had no mechanism for explaining why only specific colors should appear. There was nothing in the established laws of motion or electromagnetism that would force energy to come out in fixed amounts. Scientists tried to fit the spectral data into classical frameworks, but the effort consistently failed. The patterns were too precise, too orderly, and too stubborn to be explained away. The breakthrough came when physicists began to take the spectral evidence seriously as a guide rather than an inconvenience. Instead of asking how spectra could fit existing theory, they asked what kind of atomic structure would naturally produce such spectra. This shift in perspective was crucial. It meant letting light lead the way, allowing experimental facts to shape theory rather than the other way around. The key insight was that light emission must correspond to changes within the atom. If atoms emitted only certain energies of light, then their internal energy must also be restricted to certain values. Each spectral line represented a specific transition between two internal states of the atom. Light, in this sense, was acting as a messenger, carrying information about these transitions to the outside world. By decoding this message, scientists could infer the structure of the atom without ever seeing it directly. This idea transformed spectroscopy from a descriptive tool into a powerful probe of atomic structure. Measuring spectral lines became a way of mapping the internal energy landscape of atoms. The spacing between lines revealed the spacing between energy states. The intensity of lines provided clues about how often certain transitions occurred. Even subtle splittings in lines hinted at additional layers of structure. Light was not just revealing that atoms had structure, it was revealing the details of that structure with remarkable precision. The relationship between light and atomic transitions also explained why atoms absorb light in specific ways. When light of a particular energy strikes an atom, it can be absorbed only if that energy matches the difference between two allowed internal states. If the energy does not match, the light passes through unaffected. This selective absorption further reinforced the idea that atomic energy states were discrete. Light was not interacting with atoms continuously but selectively, according to strict rules. This selectivity had profound implications. It meant that atoms were not passive recipients of energy, but highly constrained systems. They responded only to specific signals and ignored all others. This behavior was completely alien to classical expectations, yet it was confirmed again and again in experiments. Light, by being either absorbed or ignored, was effectively testing the atom and revealing its internal permissions and prohibitions. As understanding deepened, it became clear that light itself could not be fully understood without considering atomic structure. The interaction between light and matter exposed limitations in the classical wave theory of light. Some experiments showed that light behaved as if it came in discrete packets of energy when interacting with atoms. The energy of these packets depended on the light's frequency, not its intensity. This realization further strengthened the connection between light and atomic energy levels. In this way, light and the atom became inseparable in the development of modern physics. Neither could be fully understood without the other. Atoms revealed their structure through light, and light revealed its true nature through atoms. This mutual illumination drove physics toward a new conceptual framework that departed radically from classical ideas. Beyond its scientific importance, the role of light carried symbolic weight. Light had long been associated with knowledge and revelation, and in atomic physics, this symbolism became literal. Invisible processes inside atoms became knowable through careful observation of emitted and absorbed light. What could not be seen directly could still be understood indirectly through its effects. The study of atomic spectra also introduced a new level of precision into physics. Spectral lines could be measured with extraordinary accuracy, providing some of the most reliable data available. This precision allowed theories to be tested rigorously. Small discrepancies between predicted and observed lines signaled the need for refinement. Light became a strict judge, rewarding accurate theories and exposing flawed ones. Over time, this approach reshaped scientific methodology. It demonstrated the power of indirect evidence. Even when direct observation is impossible, structure can be inferred from patterns. The atom taught scientists that reality does not have to be visible to be measurable, and that careful interpretation of signals can reveal hidden order. The legacy of light's role in revealing atomic structure extends into modern technology. Lasers, spectroscopy, and atomic clocks all rely on precise control and measurement of atomic transitions involving light. These technologies are practical expressions of insights first gained by observing spectral lines. What began as a puzzle about colored lines became a foundation for much of modern science and engineering. In the end, light did far more than illuminate atoms in a metaphorical sense. It provided the evidence that forced a new understanding of matter. Through its selective emission and absorption, light exposed the discrete internal structure of atoms and showed that energy at the microscopic level follows strict rules. By listening carefully to the messages carried by light, physicists uncovered a hidden order within the atom, transforming mystery into knowledge and opening the door to the quantum world. The ideas that emerged from early atomic theory did more than solve isolated problems. They formed a critical bridge between two very different ways of understanding nature. On one side stood classical physics, built on continuity, determinism, and familiar mechanical ideas. On the other side lay the emerging quantum view, marked by discreteness, probability, and abstract rules. The importance of this transition lies not in the rejection of classical physics, but in how the new ideas connected the old world to the new, allowing science to move forward without collapsing its entire foundation. Classical physics had been extraordinarily successful in describing motion, forces, and energy at everyday scales. Planets followed predictable paths, machines behaved reliably, and waves of sound and light could be calculated with precision. This success created a strong expectation that the same principles should apply universally. Early atomic models were therefore deeply rooted in classical concepts. Electrons were imagined as particles, forces acted continuously, and motion followed clear trajectories. These assumptions provided a familiar starting point, even as experiments began to show their limits. The new atomic ideas did not immediately discard this classical language. Instead, they reshaped it. Concepts such as orbits, energy, and radiation were retained, but they were constrained in ways that classical physics had never allowed. Energy could no longer take any value it pleased. It was restricted to specific amounts. Motion was no longer described solely by continuous paths, it was defined by allowed states. These changes preserved enough of the old framework to remain intelligible, while introducing rules that resolved experimental contradictions. This blending of old and new was crucial. A sudden, complete break with classical physics would have left scientists without conceptual tools. By keeping familiar terms but redefining their meaning, atomic theory provided continuity during a period of upheaval. Physicists could still speak of electrons and energy, but they had to accept that these concepts behaved differently at microscopic scales. The bridge allowed gradual adaptation rather than abrupt replacement. One of the most important aspects of this transition was the reinterpretation of classical failure. Instead of viewing classical physics as wrong, it was reclassified as incomplete. Its laws were seen as approximations that worked extremely well under certain conditions, but failed under others. This perspective preserved the achievements of classical physics while acknowledging its limits. It also introduced a more flexible view of scientific truth, in which theories are judged by where they work rather than whether they are universally valid. This shift had deep methodological consequences. Physicists learned to think in terms of domains of applicability. A theory was no longer expected to explain everything. It was expected to explain something well. When applied outside its proper domain, failure was not a scandal but a signal that a different framework was needed. This attitude became central to modern science and continues to guide research today. The bridge between classical and quantum thinking also reshaped expectations about explanation. Classical explanations relied heavily on mechanical stories. Forces caused accelerations, which produced motion along definite paths. Atomic theory showed that such stories could not always be told. In their place came rules about allowed states and transitions. Explanation became less about visual narratives and more about mathematical structure and empirical consistency. This change did not make physics less explanatory. It changed what explanation meant. Another important element of this bridge was the coexistence of certainty and uncertainty. Classical physics offered certainty in prediction, while atomic theory introduced probability. The two were not mutually exclusive but complementary. At large scales, probabilities average out and classical certainty emerges. At small scales, probabilities dominate. This realization unified the two perspectives into a single layered view of reality. Determinism was not destroyed, it was contextualized. The transition also influenced how physicists thought about reductionism. Classical thinking often assumed that understanding smaller parts automatically explained larger systems. Atomic theory showed that this was not always straightforward. New properties could emerge at different scales, governed by rules that were not obvious from lower-level descriptions. This insight enriched scientific thinking by emphasizing the importance of structure and organization, not just fundamental components. Educationally, the bridge played a vital role. Students could learn classical physics first, building intuition and mathematical skill, before encountering quantum ideas. The new concepts could then be introduced as refinements rather than replacements. This layered learning mirrored the historical development of physics itself, reinforcing the idea that knowledge grows through extension and correction rather than sudden leaps. The influence of this bridging role extended beyond physics. Other sciences adopted similar attitudes toward theory and explanation. In chemistry, classical models of bonding were revised using quantum ideas. In biology, classical mechanics gave way to molecular and statistical descriptions where appropriate. The lesson that different levels of reality require different tools became widely accepted. Technologically, this bridge proved immensely productive. Engineers could continue using classical principles to design machines and structures, while quantum principles guided the development of new materials and devices. Semiconductors, lasers, and modern electronics exist precisely because scientists learned how to move between classical and quantum descriptions depending on the problem at hand. The coexistence of the two frameworks became a practical advantage rather than a theoretical inconvenience. Philosophically, the transition encouraged a more modest view of human understanding. The belief that nature must conform to intuitive ideas was replaced by the recognition that intuition is shaped by limited experience. Reality, especially at extreme scales, may not be directly imaginable. Accepting this did not weaken science, it strengthened it by freeing inquiry from unnecessary constraints. The bridge between classical and quantum physics also demonstrated the creative power of compromise. Instead of choosing between old and new ideas, physicists combined them in novel ways. This willingness to adapt rather than reject allowed progress to continue even in the face of deep conceptual tension. It showed that revolutions in science can be constructive rather than destructive. Over time, the transitional models themselves were refined and eventually replaced by more complete quantum theories. Yet their historical role remains essential. They made the unfamiliar approachable and the radical acceptable. Without them, the leap into full quantum mechanics would have been far more difficult, both intellectually and psychologically. In the end, the importance of this bridge lies in what it reveals about scientific progress. Knowledge does not advance by erasing the past, but by building upon it while correcting its limits. The transition from classical to quantum thinking illustrates how science evolves through dialogue between old ideas and new evidence. It shows that understanding deepens not by clinging to certainty, but by remaining open to change. This lesson continues to resonate. Modern physics still operates at the boundaries between established theories and emerging ideas. The story of how atomic theory bridged classical and quantum worlds serves as a reminder that the most fruitful advances often occur in these transitional spaces. By embracing both continuity and change, science finds its way forward, expanding its reach while honoring the insights that made progress possible. The atomic model that introduced fixed energy levels and simple rules for electron behavior achieved remarkable success, yet it was never presented as a complete or final description of reality. From the beginning, its limitations were apparent, and these limits played a crucial role in driving physics forward. Understanding where the model failed is just as important as recognizing where it succeeded, because those failures revealed deeper truths about the nature of atoms and guided the development of more powerful theories. One of the earliest signs of limitation appeared when scientists tried to apply the model beyond the simplest atom. While it worked beautifully for hydrogen, which contains only one electron, it struggled with atoms that had multiple electrons. In these more complex systems, electrons interact not only with the nucleus, but also with each other. These interactions create a web of forces that the simple framework could not handle. Predictions became inaccurate, and spectral lines no longer matched experimental data with the same precision. This showed that the model captured something essential but incomplete. Another limitation lay in its reliance on sharply defined orbits. The idea that electrons move in neat circular paths was useful for calculation and visualization, but it conflicted with emerging experimental evidence. As measurement techniques improved, it became clear that electrons did not behave like tiny planets following predictable tracks. Their behavior exhibited wave-like properties that could not be reconciled with fixed paths. The orbit picture was an approximation that worked only under restricted conditions. The model also could not fully explain the fine details observed in atomic spectra. High-resolution experiments revealed subtle splittings and shifts in spectral lines that went beyond simple energy differences. These effects depended on factors such as electron spin and relativistic corrections, none of which were included in the original framework. Each new discrepancy highlighted another layer of atomic complexity that demanded a more sophisticated approach. Despite these shortcomings, the importance of the model did not diminish. On the contrary, its limitations became a source of insight. By clearly defining what the model could and could not explain, physicists gained a roadmap for future research. The gaps pointed directly to the questions that needed answering. Instead of being obstacles, the failures became guides. One of the most profound contributions of the model was its demonstration that classical ideas had to be modified at the atomic scale. Even where the model failed, it succeeded in breaking the assumption that electrons must obey classical mechanics. This conceptual shift was irreversible. Once scientists accepted that classical rules were not universally valid, they were free to explore new principles without trying to force atomic behavior into an outdated framework. The model also mattered because it introduced quantization as a central concept. Even when later theories replaced fixed orbits with more abstract descriptions, the idea that energy levels are discrete remained intact. This concept survived every refinement and became a cornerstone of modern quantum mechanics. The original model served as the first clear demonstration that quantization was not a mathematical trick, but a real feature of nature. Another reason the model mattered was its pedagogical power. It provided a clear and accessible way to think about atoms during a time of conceptual upheaval. Scientists and students alike could grasp its basic ideas without advanced mathematics. This accessibility allowed the new quantum perspective to spread rapidly, shaping how generations learned about atomic structure. Even today, simplified versions of the model are used as stepping stones to more advanced theories. The limitations of the model also helped redefine what a scientific model is meant to do. It showed that a model does not have to be perfectly accurate in every detail to be profoundly useful. A model can be valuable if it captures key relationships and makes correct predictions within a certain domain. This pragmatic view of modeling became standard practice in science, influencing fields far beyond physics. Historically, the model marked a turning point between intuition-based and principle-based explanations. Its assumptions were not derived from everyday experience, but from experimental necessity. When it worked because it matched observation, not because it made intuitive sense. When it failed in ways that exposed deeper layers of structure. This balance between success and failure made it an ideal transitional framework. The importance of its limits is also evident in how they motivated the development of new ideas. The inability to describe electron interactions led to the exploration of wave-like behavior. The failure of fixed orbits opened the door to probability-based descriptions. Each limitation pushed physicists to abandon another classical assumption, gradually building the foundations of a more complete quantum theory. In this way, the model functioned like a scaffold. It was not meant to remain standing forever, but without it, constructing the final structure would have been far more difficult. Once the building was complete, the scaffold could be removed, but its role remained essential to the process. The story of this model illustrates a broader truth about scientific progress. Advances often come from imperfect ideas that are good enough to move understanding forward. Perfection is not a prerequisite for significance. Sometimes, the most influential theories are those that clearly show both what we know and what we do not yet understand. In retrospect, the limitations of the atomic model are not signs of weakness, but signs of depth. They reveal how close physics came to the boundary of classical understanding and how boldly it stepped beyond it. The model mattered not because it was the final word on atomic structure, but because it changed the questions scientists asked and the answers they were willing to accept. By highlighting where classical intuition failed and where new principles were needed, the model accelerated the transition to modern quantum mechanics. It taught physicists to respect experimental evidence over visual simplicity and to accept abstraction when reality demanded it. Its legacy lives on not in its specific details, but in the mindset it fostered. Ultimately, the value of the model lies in its role as a bridge and a catalyst. It connected old ideas with new evidence, clarified fundamental problems, and inspired solutions that went far beyond its original scope. Its limits were not the end of its usefulness, but the very reason it mattered so deeply in the history of science. The influence of Niels Bohr extends far beyond the specific details of his atomic model. His true legacy lies in how he transformed the way science thinks about nature, knowledge, and explanation. Through his ideas, physics entered a new intellectual era, one that reshaped not only atomic theory, but the entire scientific worldview. The impact of this transformation continues to be felt in modern science, technology, and even philosophy. One of Bohr's most enduring contributions was his insistence that scientific theories must respect the limits imposed by nature, even when those limits conflict with intuition. He understood that the goal of physics was not to preserve familiar pictures, but to describe what experiments reveal as faithfully as possible. This attitude encouraged a shift away from mechanical explanations toward principle-based reasoning. Instead of asking how something happens in terms of classical motion, physicists began asking what conditions and constraints govern possible outcomes. Bohr played a central role in shaping the conceptual foundations of quantum theory. His ideas emphasized that atomic phenomena require new forms of description that cannot be reduced to classical terms. He argued that attempts to force atomic behavior into familiar categories would inevitably fail. This perspective helped physicists accept the strangeness of the quantum world rather than resist it. The acceptance of uncertainty, discreteness, and probability as fundamental features of nature owes much to Bohr's intellectual leadership. Another crucial aspect of his legacy is the principle of complementarity. Bohr proposed that certain properties of quantum systems cannot be observed or described simultaneously, even though each is necessary for a complete understanding. This idea challenged the classical assumption that all properties of a system can, in principle, be known at once. Complementarity introduced a new way of thinking about knowledge itself, one that acknowledges the role of experimental context in shaping what can be known. This insight had profound philosophical implications. It suggested that scientific knowledge is not a simple reflection of reality, but a structured interaction between observer, experiment, and system. Bohr did not argue that reality is subjective, but that our access to it is constrained. This subtle distinction influenced debates about objectivity, realism, and the nature of scientific truth. His views continue to be discussed and debated by philosophers of science today. Bohr's influence was also institutional. He created an environment that nurtured some of the greatest scientific minds of the 20th century. His institute became a gathering place for young physicists who would go on to develop the full mathematical framework of quantum mechanics. By encouraging open discussion, critical questioning, and collaboration, Bohr helped establish a culture of inquiry that accelerated progress. His role as a mentor and facilitator was as important as his personal contributions. The practical impact of Bohr's ideas is visible throughout modern technology. The understanding of atomic structure and energy levels underlies countless applications, from electronics to medical imaging. Lasers, transistors, and atomic clocks all rely on principles that trace back to the quantum view of atoms that Bohr helped establish. These technologies have transformed daily life, global communication, and scientific research. Bohr's legacy also includes a new understanding of scientific humility. He recognized that theories are tools, not final truths. This recognition did not undermine confidence in science, it made science more resilient. By accepting that models have limits, physicists became better equipped to adapt when new evidence emerged. This flexible attitude remains one of the strengths of modern scientific practice. Beyond physics, Bohr's ideas influenced how other fields think about complexity and knowledge. The notion that different descriptions may be necessary for different aspects of a system has parallels in biology, psychology, and social sciences. Complex systems often require multiple perspectives that cannot be fully unified into a single description. Bohr's work provided a conceptual precedent for this kind of pluralism. Historically, Bohr's contributions marked a turning point between two eras of science. Before him, physics sought to explain everything in terms of continuous motion and deterministic laws. After him, physics embraced probability, abstraction, and limitation as fundamental features of reality. This shift did not diminish the power of science, it expanded it. It allowed physicists to explore realms that were previously inaccessible. The emotional and intellectual courage required for this shift should not be underestimated. Accepting that nature operates in ways that defy intuition demands a willingness to rethink deeply held beliefs. Bohr exemplified this courage. He did not cling to comforting ideas when evidence contradicted them. Instead, he invited discomfort as a necessary part of discovery. Bohr's approach also highlighted the importance of dialogue between theory and experiment. He believed that neither could advance alone. Theory must be guided by observation, and experiments must be interpreted through theory. This balanced view helped prevent extremes, ensuring that physics remained grounded in reality while exploring abstract concepts. In the broader cultural context, Bohr became a symbol of modern scientific thought. His work challenged simplistic views of certainty and control, resonating with a century marked by rapid change and uncertainty. The quantum worldview influenced not only science but also art, literature, and philosophy, shaping how people thought about order, chance, and meaning. Even today, debates about the interpretation of quantum mechanics often return to Bohr's ideas. His emphasis on complementarity and contextuality continues to inform discussions about measurement, reality, and information. While new theories and interpretations have been proposed, the foundational questions he raised remain central. Ultimately, Bohr's lasting impact lies in the mindset he helped establish. He taught scientists to accept that understanding does not require complete visualization, that precision does not guarantee certainty, and that knowledge has inherent limits. These lessons extend beyond physics and apply to any serious attempt to understand complex systems. The story of Bohr and the atom is therefore not just a chapter in the history of science, but a lesson in how knowledge evolves. It shows that progress often comes from embracing paradox rather than resolving it prematurely. It reminds us that the universe may be deeper and stranger than our everyday experience suggests, yet still governed by discoverable laws. Through his work, Bohr helped transform physics from a search for mechanical certainty into an exploration of structured possibility. His legacy endures in the theories we use, the technologies we rely on, and the intellectual humility that guides scientific inquiry. In reshaping how we understand atoms, he reshaped how we understand understanding itself.